Let's talk about centrality. In his classic 1978 essay, Lynn Freeman laid out three different notions of centrality. The first is degree centrality, which captures the idea that individuals with many contacts are central to a social structure. This measure is calculated simply as the degree of the individual actor, that is, the number of edges that are incident to the vertex. Closeness centrality captures the idea that a central actor will be close to many other actors in a network. Closeness is measured by the geodesics between actor I and all others, geodesics being a shortest path in a graph. Betweenness centrality also uses geodesics, and it captures the idea that a highly central individual should be on the shortest paths between other pairs of actors in a network. The betweenness of actor I is simply the fraction of all geodesics in the graph on which I falls. So let's look briefly at the calculation of these things. For non-directed graphs, the degree centrality of vertex I is simply the sum of all the edges that are incident to vertex I. Right? So we can indicate degree centrality as C sub d, centrality of degree. Right? Of vertex I, it's just the degree of vertex I, which is just the sum across all j not equal to I of edges that are incident to vertex I. Note that while we call this a centrality measure, it's simply the degree of node I. Sometimes degree centrality will be standardized by the size of the graph, which we can indicate as n. So we'll divide our degree centrality by n minus 1, where we subtract 1 from the size of the graph to account for the actor itself. Closeness centrality. For non-directed graphs, the closeness centrality of vertex I is the inverse of the sum of the geodesics between vi and vj, where vi and vj are vertex I and vertex j, for all j not equal to I. Okay, so we have a distance metric, which is just the minimum distance, or the geodesic, between vertices I and j. We sum those up, and we invert that measure. Now we should note that if j is not reachable from I, then the closeness centrality will equal 0, since the distance between I and j is infinite. This means that we often want to restrict our measurements of centrality when we're using closeness to connected components of the graph, and it can limit the types of applications to which you can apply closeness centrality. To standardize this, we can multiply by n minus 1 the number of vertices not including I. Betweenness centrality. For non-directed graphs, the betweenness centrality of vertex I is the fraction of all geodesics, or shortest paths, in the graph on which I lies. Okay, so gjk is the number of geodesics linking actors j and k, and bear in mind there can be multiple of these. In a closely, like in a tight graph, in a dense graph, there often will be multiple geodesics between j and k. And gjk of vi is the number of geodesics linking actors j and k that contain actor I. So that's our numerator, and then we divide by the sum of all the geodesics, and we sum across all j less than k. That's our betweenness centrality. We can standardize this by dividing by the number of pairs of actors not including I. And bear in mind that the number of unordered pairs in a graph is equal to n times n minus 1 divided by 2. And so if we subtract away 1 for accounting for individual I, then we have n minus 1 times n minus 2 divided by 2 as our scaling factor. Okay, so both closeness and betweenness use geodesics, or minimum paths, as the distance metric for calculating centrality. You can imagine that other paths matter as well, and there are a number of extensions of Freeman's centrality measures. An early one was introduced by Stevenson and Zellin in 1989, and they call it information centrality. And substantively, it captures the notion that a central person is someone who knows people who know a lot of people. It's sort of a second order type of measurement. The calculation of information centrality is a little more complicated than for the others because we have to actually write a function for it. It's not included in iGraph. But it's just pretty basic linear algebra. We start with a sociomatrix X, and from this we calculate an intermediate matrix A. And A is pretty straightforward. The diagonal elements of A, so the AII, are simply the degree of vertex I plus 1. Okay, so that's the diagonal of A. And then the off-diagonal elements of A are just the complement of the sociomatrix. So if there's a 1 in the ijth cell of matrix X, the sociomatrix, there's a 0 in matrix A, and vice versa. Once we've calculated A, we invert it to yield a new matrix C. We calculate T, the trace of C, which is simply the sum of its diagonal elements, and R, which is a row sum of C. All the row sums will be the same for C. With those things all together, we have a formula here for information centrality. And we can then write a simple little function to calculate that. The function is in the notes, so I won't linger over it. It's just a straightforward rendering of the information centrality formula. We'll talk about one other centrality measure. There are actually quite a few newer ones, but these are in common usage in social network analysis and give you a flavor for the types of measures that we can do trying to identify central individuals in a graph. Phil Banasic in 1972 suggested that the eigenvectors of a sociomatrix are a fruitful way of looking at centrality. As with information centrality, the eigenvector approach captures the idea that central people will have well-connected alters, but that the relative importance of these alters falls off with distance from ego. While the eigenvector of a sociomatrix is an excellent measure of centrality, in 1987, Banasic suggested a slightly more complex measure that is what most people use today when they talk about eigenvalue centrality. There are two parameters, and this is derived just from the eigenvalues of the sociomatrix. There are two parameters, alpha and beta, and the key parameter here is beta. Alpha is sort of just a scaling factor. Beta measures the extent to which an actor's status is a function of the statuses of its alters and how that decays from the focal actor. So in the formula here, we've got the scaling factor I, we've got beta, which measures this decay of influence as you move away from ego. I is just an identity matrix, and 1 is just a column vector of 1s. We do a little linear algebra, we calculate that. The size of beta determines the degree to which the Banasic centrality is a measure of local or global centrality. When beta is equal to 0, only an actor's direct ties are taken into account. And so we can see that Banasic centrality becomes proportional to degree centrality. When beta is greater than 0, an actor's alters ties are also taken into account. The larger the value of beta, the more that distant ties will matter for ego's centrality. It's interesting to note that it's also possible for beta to be less than 0. In this case, being connected to powerful alters who themselves have many alters negatively affects an actor's status. This might seem a little bizarre at first blush, but the situation captures the effect observed in bargaining experiments performed by Karen Cook and her colleagues in 1983, where an individual's ability to negotiate a favorable outcome is lessened when he or she must bargain with powerful, well-connected alters. All right, so those are the centrality measures that we're going to think about. We'll do a couple quick calculations to compare these, and we'll use John Paget's Florentine marriage data. Um, I'll just note that for these analyses, we'll take out the Pucci family since they're an isolate. And we'll use only the connected component using decomposed graph and keeping only the first component. For the standard centrality measures discussed by Freeman, Pucci will have a score of 0. And for information and eigenvalue centrality, those measures only work on connected graphs. So we have to just focus on the connected subcomponent. Okay, to R. There are lots of different places to get the Florentine marriage data. I have it listed here in the class webpage, so we can read that in. And and we better, oops, got to go down here. Didn't do that. All right. Let's look at flow. It's a binary matrix where a 1 indicates that there's a marriage tie between two families. In iGraph, we'll create a graph object from the adjacency matrix. So we'll call it gflow, graph from adjacency matrix. We'll also just make sure that flow is a matrix, because when you use read table, right, it'll read it into R as a data frame by default. So we just coerce it into being a matrix, and we indicate that its mode is undirected, because it is an undirected relation. We've got that there. We can take a gander at it. We got 16 vertices. We've got 20 edges. Okay. We can plot that if we like. Always a good idea to plot your data. And we can see that Pucci is an isolate out here. So we'll use decomposed graph to work on only the connected component. We'll see that the majority of the families are in fact connected. So we'll decompose graph, and we'll take the first element of that output list. Okay, and let's have a standard layout. So we'll do a layout with Fruchterman-Reingold that we can refer to later on. We will now replot our decomposed graph. We'll take away the names because they get a little busy. Okay, and for the information centrality function that we wrote, it takes a matrix. It doesn't take a graph object. So we'll go back to flow 1, and we'll remove Pucci, who happened to be the 12th element, row and column. All right, and I should show you information centrality, and I should also load it into R. Here's the function. There it is. Okay. So we can calculate that, and we can calculate Banasich power centrality, which is his derived eigenvalue measure. Call it CE. We'll take the absolute value of that. It's an iGraph function, power centrality. It takes a graph as an object, as an argument. And then we'll just put together a series of, probably should have turned off my email. Let's see if we can finish without too many more coming. We'll do that. So we're calculating degree, betweenness, closeness, and then we're adding in the two we just calculated, the information centrality and the Banasich eigenvalue measure. We'll give them the dim names of the family names from the Florentine marriage data, and we'll look at these. So we have as columns all the different centrality measures, and as the rows the different families. And of course, we'll see that if we look across, that the Medici frequently have the highest centrality measures because they're quite central to the network. What's interesting, though, is that they don't have the highest eigenvalue centralities because they're so central, they're so connected. The families to whom they are connected through marriage are necessarily less powerful, right? Because the Medici are actually so dominant. So that families who are connected themselves to the Medici, the Albizzi, for example, seem to benefit a lot from this, have higher eigenvalue centralities than the Medici themselves. But of course, the Medici really dominate in the other centrality measures. We can look at the correlations across the different measures. Just create a correlation matrix. And we'll see that they tend to be pretty well correlated with each other. But, variably. And interestingly, if we look at the last column of this, the eigenvalue centrality is clearly capturing something quite different than the other measures of centrality, including information centrality, which, of course, generalizes beyond the geodesics into looking at longer paths. But it shows that this idea of counting geodesics is actually pretty robust, at least in this simple network. Whereas the eigenvalue centralities are quite different, and are clearly getting at a different type of measure of power. And something that's nice to do with centralities, you can do this in iGraph, is to use a centrality as information for changing the plotting size, the vertex size of your plot. So we can do that with a betweenness centrality. We'll add 1 to it because there is one family that has a betweenness centrality of 0. Okay, so we'll add 1 to it so that we have non-zero vertex size for all of them, and look at what we can do. Right, so there's a cool way to visualize the centrality of the Florentine marriage data. I'm going to call it quits there. We'll probably talk about centrality quite a bit more later on.